8th graders, today's assignment is a 3.3 thermal energy assignment. Your learning targets: I can relate the amount of thermal energy of an object to how much energy it has to transfer in a system. So basically what we're saying is the more thermal energy something has, the more energy it can potentially transfer to another object if they come into contact to reach equilibrium. Okay. All right. So in this lab, you guys are going to, or excuse me, in this assignment, you guys are going to be doing a little mini lab where you guys have to watch a video in the background while you work. Okay. So we're going to go ahead and move on to warm up because this is going to set the stage for our little demo that you'll be watching today. All right. So predicting changes in water samples. Today you will see a demonstration of energy transfer that uses the setup pictured on the right. Look over the diagram and decide whether you agree or disagree with the predictions on the next slide. So we have system X consists of cup X, submerged, and container X. Container X has 100 milliliters of cold water. Cup X has 100 milliliters of hot water. Okay, system Y, on the other hand, has 300 milliliters of hot water in the Y cup, which is submerged in the Y container, holding 100 milliliters of cold water. Okay, so you guys are going to use your draw tool for this part, and you're going to mark each statement with whether you agree or disagree. Just a reminder for you guys, anytime you guys see a question mark somewhere on your slide, there's something you guys have to do, so make sure you complete everything. I've been seeing a lot of kids just not completing assignments because they're missing pieces here or there, and for that they're not getting full credit. Okay, so the water in cup X will end up at the same temperature as the water in cup X. Or excuse me, container X. So you either agree with that statement or you disagree. The water in cup Y will end up at the same temperature as the water in container Y. Agree or disagree. And then all of the water in both containers and cups will end up at the same temperature. Agree or disagree. Okay, all right, moving back along. Make sure you click back on your cursor when you're done using your draw tool to circle agree or disagree there. We're going to go ahead and start this demo on slide 4. So those of you guys who are doing this from home, you guys will be watching this video, and you guys, I'll explain this in the beginning of the part of the video for you guys, is you don't have to sit and watch this. It's like a 40-minute video. It's like watching paint dry. But what I do want you guys to do is every time you guys hear the timer go off in the background, you guys will pause this video, pause what you're doing in the assignment, and you'll flip into that other video, and you guys will use that video to collect your data. So it's over a 30-minute time period, and it takes me about 5-10 minutes to get it set up. So over about 40 minutes, you guys will be listening for the timer to go off. I'll get your guys' first reading right before we start. And then every 5 minutes, you'll hear the timer go off in the video. So again, pause what you're doing here, move on to that other video. Those of you guys in class, though, you guys will be doing this in class and taking turns as groups to record your data on the board and getting this as a whole. So you guys will be coming back to this little table on slide 4 a lot to enter in your 5-minute data from 0 to 30 minutes. Okay, so again, you guys will be collecting temperature for the cup X, container X, cup Y, container Y over a 30-minute time period every 5 minutes. Okay? All right, moving on. You guys are going to demo this in the Sim 2 as well. So you guys can see your direction here. You're going to first set up system X. So we can't really put something inside another object, but in the Sim we can make them come into contact. So system X, 100 milliliters of cold water, 100 milliliters of hot water. So remember we had hot water in the cup, cold water in the container. In this case, we're just going to use 2 objects, one that's cold and one that's hot, and notice they are the same size. So you guys can go ahead, right-click the Sim link down here, open it up. Looks something like this. All right. So in the thermal energy sim, add a medium-sized sample to represent the water in container X. Cool this sample to 4.5 degrees Celsius. So I'm going to go ahead, medium sample. I'm going to confirm that. I'm going to cool it down to 4.5 degrees Celsius. I want to see my kinetic energy as well because that kind of helps me, and I also want to see my energy transfers. Okay, and then my second one, record the starting, add a medium sample, so this is going to be sample B to represent the water in cup X. So this is going to be warm water. This has been what goes in the cup. So that's going to be 38.6 degrees. So same size sample, except they were going to heat this one up and make it 38.6. Okay? All right, so you guys can see how the molecules are moving differently. You guys can see the differences in the kinetic energy based on the color and their movement. And then you guys can also notice that the thermal energy for each of these samples is different, as well as the temperature. Okay, remember from last lesson you guys learned that thermal energy is the total amount of kinetic energy for all the molecules in an object, versus temperature, as we've learned, is the average. Okay, so total should be a little bit bigger of a number. All right, finally, record the starting thermal energy of both samples below. So you guys will see this little data table here. So we already know the starting temperatures because we set them at that. Starting thermal energy for this one is going to be 15 and 90. So sample A is 15, sample B is 90. And then the system. So because we haven't really pushed them together yet, we're going to go ahead and calculate the system manually. So add the starting thermal energies for sample A and B. So we're going to take 15 plus 90, that should be about 105. And we're going to record that right here as the system. Okay? And then what we're going to do is we're going to push those two together. You guys will notice that this yellow arrow represents the energy transfer. When this yellow arrow disappears, energy is done transferring and your system has reached equilibrium to the point at which all those molecules have an average kinetic energy that's the same. So I'm going to go ahead and pause that. You guys note that you can also change the speed of this. So if you're sick of watching this little yellow arrow and thinking nothing's really happening as these numbers slowly change, you guys can go ahead and change your speed to a greater speed to kind of help you guys out a little bit more, there. And then again, when that yellow arrow goes away, you have reached equilibrium and you can go ahead and record your final data. So your ending temperature, what is it? And then your ending thermal energy, what is that? So for sample A, sample B, if they're at equilibrium, what do you guys know about the ending temperature and even maybe the thermal energy there? What can you guys observe about that? Definitely your ending temperature though. And then add the ending thermal energies for sample A and B to find the ending thermal energy for the system. So add up this box plus this box and that will be your system's thermal energy. All right, now you guys are going to do the exact same thing, but you guys are going to model system Y, where we had 100 milliliters of cold water in the container and 300 milliliters of hot water submerged with the cup inside that container. So you guys are going to use a medium sample for sample A. That's going to be container Y. You're going to cool that. So that's your cup. That's your, or excuse me, your container, your bowl, whatever you guys want to call it. And then add a large sample, sample B, to represent the water in cup Y. Warm this to 38, so we're going to have a much larger sample here. Record your starting. Same thing with this, where you guys add up your guys' thermal energy for the system for both of these. And then you guys, same thing, you'll push those two together. Watch that little yellow arrow until it disappears, and then record your ending temperature and your ending thermal energy for each sample in that system Y. Okay, and then answer these three questions. Kind of skips around, so it goes here and then down to the bottom, then up here. In both systems, so X and Y, how did the starting thermal energy compare to the ending thermal energy? So look at the thermal energy for that system before and after. Okay? Question 2, which system reached a higher equilibrium temperature? Which one had a higher temperature at the end of it all? Okay, system X, system Y, or if they were both the same, I want you guys just to take a marker in your draw tool and write the same, if they are the same. Okay? And then finally, question 3. Why do you think this system, so whatever you guys answered for this one, why do you think this system reached equilibrium at a higher temperature? So tell me a little bit about that and what you guys know based on these 3 questions. All right, moving on. You guys have a little goal to, or a little task, if you will, to answer. So if you were in charge of deciding how to heat a school, okay, you guys are going to use what you know about thermal energy and energy transfer to figure this little problem out. Okay, so the groundwater tank holds exactly 3 times as much water as the heated water tank. So you have 2 options here. You can either use this heated water tank, where it pumps water around these little coils in the school, and that water tank is about 1/3 the size of this groundwater tank. So if it's 11 degrees Celsius outside, which is a fairly cold winter day, okay, we have water inside of this water heater that's 39 degrees Celsius. That's slightly above body temperature. Okay, and then over here, if again we still have the same morning temperature, we have this groundwater system that the water is only about 30 degrees Celsius. So slightly warmer than room temperature, lower than body temperature. but we have a 3-time larger system there. So kind of like you guys saw in the demo today, as you guys are working through that, and in the simulation that you guys just did of the demo, okay, you have a system that has 3 times as much, but the temperature isn't as high as our little tank here. So I want you guys to take a guess which system you guys would think would be better, and then we're gonna go ahead and double check that in the sim. Okay, so use the sim to answer the chapter 3 question, which heating system will warm the air in the school more? So you guys obviously won't be working necessarily with a partner, but you guys in class can check with a partner if you'd like. So run 2 separate tests and compare the results. Then write your answer to the question below. So test 1, you guys are gonna test out the first heater here, where we have slightly warmer tank, but it's smaller. So in the thermal energy sim, add a large sample to represent the air inside the school. Cool this to 11.4 degrees Celsius. So we're going to assume the air inside the school has kind of normalized to what the temperature outside is. And add a small sample to represent the water in the water heater. Warm this sample to 38.6 degrees Celsius. Okay, so very similar to what you guys just did. You guys are going to see how much this little warm sample can warm up this larger school, if you will. Pull the samples together and find out the equilibrium temperature and record it below. Second test you're going to run is the groundwater system. You're going to add a large sample to represent the air inside the school. Cool that to 11.4. Again, we're going to assume it's about the same temperature as the outside air after, I don't know, not being heated for a couple days or whatever the case. And then add a large sample to represent the groundwater. So last time we used a small sample, now we're using a large sample. Warm this sample to 29.5, so we're not warming it as much. Last one we warmed to about 38.6. This one we're only warming to 29.5. Pull the samples together to find out the equilibrium temperature and record it below. So you guys will record that here. Based on the findings in the sim, which system will warm the school more during the winter? So either your little heater tank or your groundwater system. And why will this heating system warm the school more? So think about, again, what you guys learned with the demo, what you guys learned with the part 3 sim, and now what you guys observed in the sim for part 4. Okay, moving on, part 5 reading. You guys have a little dilemma to read about, so you can go ahead, right click, open that link. It'll take you into the Amplify library, and you guys are going to read about how dumplings are cooked. So if you guys have ever had dumplings before at, say, like Nagoya or Jade Garden, any of those places, you guys have a couple options. You can either have them fried in oil so they're crispy on the outside, or you guys can have them boiled in water so they're a little bit softer. So remember that you guys can have Amplify read this to you if you guys click the speaker here and then click play.
Dumpling dilemma.
So listen to that article or read it. You guys don't have to highlight or annotate. And then come back and answer these 2 questions. What are 2 reasons why dumplings cook faster in oil than in water? And then secondly, what is something new you learned about temperature and thermal energy from reading this article? All right, last little part is just revisiting what you guys did in the demo and in the warm-up. So remember, you guys had this warm-up. You guys also conducted this same experiment, or are still kind of conducting this same experiment in the demo. Okay, so looking back at what you guys answered here, I want you guys to go ahead and revisit these same questions. So the water in cup X will end up at the same temperature as the water in container X, and the water in cup Y will end up at the same temperature as the water in container Y. So really, when we ask this question, we're talking about at the end of our little time frame, we did about 30 minutes. So what do you guys think? Do you think that they're all going to be the same? You either agree or disagree. And then finally, all the water in both containers and cups will end up at the same temperature. So at the end of that 30-minute time, how do you guys think that's going to look? Okay, finally, complete your wrap-up. Do you have any questions? Circle yes or no. If yes, type them below. Obviously, if it's something that's preventing you from completing this assignment, you guys want to get at me right away so I can help you out. And then how do you feel you did on this assignment? 4, 3, 2, 1. I hope you all are having a wonderful day, and I will talk to you soon.